So you have this complex variability of energy supply and an equally complex variability in consumer demand. And so you need a system. You need something in the middle that just balances the two out. So when you've got too much renewable power, a way of storing it, and when you've got too much demand, a way of giving it back. What you do by the increase in density is one of two things fundamentally. So to get the same performance with water, you can reduce the vertical elevation by, again, proportionate to the increase in density and still get the same performance. And the advantage of that is that it opens up an order of magnitude or several orders of magnitude more sites.
Welcome to Mindful Businesses, presented by Sarani, and I'm your host, Vidya Iyer. In our podcast, we bring to you brands that are mindful in their practices and processes. A mindful business adopts and employs sustainable social, economic, and environmental practices. Today, we talk with Stephen Crosher, CEO of RheEnergise, High Density Hydro. Stephen is based in London, UK, but he joins us from Warsaw, Poland. Welcome, Stephen.
Thank you very much. It's a real pleasure to be here, Vidya. Thank you very much.
Yeah, I should thank you. I know you had a long flight with delays and everything, but you made it in time for the recording.
A few delays, but yeah, no, the journey from the airport was super quick. So we had a keen Polish taxi driver who was keen to get there very quickly. So that was quite exciting.
So now on to our topic. World leaders are paying more attention now than before about the warnings about climate change, making efforts to seek energy that is not derived from fossil fuels. One of the forms of renewable energy is hydroelectricity. But even in the ancient times, the Greeks used hydropower for their flour mills. The Egyptians had water screws for irrigation. Give us a simple lesson in physics. How can we harness energy from water?
So harnessing energy from water, as you say, is a super old activity. Simple water wheels to turn flour mills or whatever. It's been out for an awful long time. The basics of it are very simple. It's the vertical elevation you have. So the further it drops, the increase in the power, and the more volume that goes down that drop, the more energy you have available. It's very much a relationship to the vertical elevation. And one of the things that hydropower did was to change it from just running down the river to being able to pump it back up again. And so you effectively created a hydropower store with two reservoirs, one at the bottom and one at the top, often with 300 to 500 meters of vertical elevation difference. I'll have to translate that into feet. So that's something like 1,000 to 1,500 feet, that sort of feeling. And the advantage of that is then suddenly you can store energy as well, or electricity. And so you pump it up and then you release it again and generate electricity back through a turbine. So it's very much an evolution of this very old.
What you are talking about is a pump storage system, is it? Or
That's right. So it's a pump storage system. So it's effectively like a big water battery that you use a mountain to sort of hold your energy. It's a simple concept, but most people are very familiar with batteries but don't necessarily know that this form of energy storage has been around for over 100 years. It's an incredibly mature technology. And first of all, it was built during the 20th century. It was generally built because you had lots of baseload power from coal and nuclear often, which was just turned on and then it was running and running and running. And if you can't use the energy when you need it, you either have to waste it or you have to find a way of using it. And so pumped hydro was built to take that excess from nuclear power or coal power fire stations, which are running the whole time, and store it overnight when people are asleep and much less power is being consumed. And then when the demand comes in the mornings and the evenings, it would be released again and provide that additional electricity for the peak powers. So that's how traditional pumped hydro works. And that was used successfully throughout lots of the 20th century across many, many parts of the world. And pumped hydropower still accounts for around 95% of the world's energy storage. And what we're doing at RheEnergise is somewhat of a little twist on that, which I'll come back to. So pumped hydropower was used to balance nuclear and coal in the 20th century. But now with the coming of renewables that we've increasingly had over the last 15, maybe 20 years, is that we have a different problem. We don't have constant base load and variable demand. We now have variable supply from renewables. So with solar, you get it during the day. You don't get it at night. If you're in the far north on world, then you get much more in the summer than you do in the winter. And then with wind, there are places which are windy and places which are not so windy. And you have this very much variable supply, electricity supply coming from renewables, which creates a different set of problems. But again, you have this mismatch between intermittent renewables, and so it can be from hydropower. So again, with hydropower, you tend to get more in the winter when there's more rain, and so you get more flow, so there's more power there, and less in the summer, and sometimes it can even stop in the summer. So you have all these different types of renewable energies, which are either seasonal or have their daily cycles, or in the case of wind, might have a twice weekly cycle. So you have this complex variability of energy supply and an equally complex variability in consumer demand. And so you need a system. You need something in the middle that just balances the two out. So when you've got too much renewable power, a way of storing it, and when you've got too much demand, a way of giving it back.
The premise of all this energy is that energy cannot be created or destroyed, only transformed. So you are taking the energy from the velocity, or rather hydroelectricity is taking the energy from the velocity of the fall of the water and taking that, capturing it, and using that to power another thing. And your invention, we'll come to it, but is so topical in my life is because mindful businesses now moved close to Niagara Falls, and where Nikola Tesla was one of the first people to transmit the electricity using AC current.
Yeah, it's one of the first huge projects was just upstream from Niagara Falls, and it's still an impressive set of engineering, and considering how long it's been there and how long it's been providing energy for, it's just amazing. And assuming it carries on raining in the northern American landmass, and then it's going to carry on being there. It will be there forever, or the potential will be there forever. Obviously, things run out. It's been an amazing source of energy for the people in that area, and will continue to be so. So it's super impressive what you can do from hydropower, but also what you can do from increasingly from other renewables, which is, Nikola Tesla was one of the people who was groundbreaking in enabling us to do this type of thing. Some of his thinking was, in advance of his time, and we've been using it for well over 100 years. So it's amazing.
So what would be the optimal elevation? Is there an optimal elevation, or is it a formula between the velocity in which the water falls down and the height? Or
the key thing about hydropower is elevation. So when you double the elevation, you double the power, or you can halve the size.
It's pretty linear, is it?
Yeah, it's entirely linear. So you can either double the elevation, and if you have the same amount of water flowing, then you'll get double the power. Or if you double the elevation, you can volumetrically halve the water flow and achieve what you did before you had double the elevation. So it's entirely linear between elevation and power, or water flow and elevation. So if you have very low, and it's called head in the hydropower industry, if you have very low head, then what you get is you need huge volumes of water. And when you go to very high head, you need much, much smaller volumes of water. So each time you double it, you can halve the volume of water. For example, our RheEnergise high-density hydro projects, we talk about an envelope between 75 and 300 metres, which is, 200 feet to 900 feet, something like that. So that's the envelope that we're talking about. But for us, a project at 75 metres is 4 times as big for the same effect as something at 300 metres. That just gives you an idea of why vertical elevation is so important. And that's true of all hydropower systems.
I've visited Niagara Falls like 3 or 4 times the last few months, and every time it's breathtaking. It's spectacular.
I mean, in terms of hydropower projects, it's not super high, but in terms of the volume of water, it's absolutely huge.
Hence, we are able to get the electricity, we were able to get as much hydropower from those falls.
Exactly, yes.
So what is the density of water?
Your American listeners are going to hate me because they're going to have to Google how to translate it. So the density of water is 1 litre of water. So this is 10 centimetres by 10 centimetres by 10 centimetres of water. 1 litre is 1 kilogram. 1 cubic metre of water is 1 tonne. So it's the metric system makes it super easy to work out what the density of water is, and 1 tonne of pure water is how the metric system is derived in terms of weight. So that's, find something common and use that to base your weight system off. So that's how it's done.
The density of water is the base for other densities.
That's right. Something like seawater is slightly denser. So if you had a cubic metre of seawater, then it's probably 1,050 kilograms. So it's so the salts in it effectively increase the density slightly. When you increase the density of something, you get an increase in performance equivalent to the increase in the density. And again, it's an entirely linear relationship, which is what we're trying to do at High Density Hydro, or RheEnergise, doing our High Density Hydro solution, which is to increase the density, which means we can make projects smaller or reduce the vertical elevation.
So if you increase the density of water, would the amount of electricity that you're able to generate change?
So what we're doing is it's an entirely mechanical systems in terms of it. So you pump this high density fluid up. It takes more energy to pump it up than you would take to pump up water. The density of our fluid is 2.5 times the density of water. So this is just over the density of concrete. So it's significantly different. And so we have a fluid we'll call it the density of concrete that we're pumping up. So that takes more energy than it would for water. So the increase of energy it takes is proportionate to the increase in density. So 2.5 times more energy to pump it up. And then when it's up there, you have 2.5 times more energy than you would have had with water. And so when you release it, you effectively generate at 2.5 times the rate that you would with water. So the round trip efficiency is the same as you would get with water. So your audience might be going, well, why bother then? If the round trip efficiency is the same. What you do by the increase in density is one of two things fundamentally. So to get the same performance with water, you can reduce the vertical elevation by, again, proportionate to the increase in density and still get the same performance. And the advantage of that is that it opens up an order of magnitude or several orders of magnitude more sites. So when we're driving in our cars or going on the train or whatever, we know that there are many more hills at, say, 300 feet than there are at 750 feet.
That's really fascinating. Where are the possible locations of your solution?
You can deploy your energy storage, your water battery type projects or your high density hydro battery type projects close to where you need them. So you can co-locate them with wind farms, or you can have them near to solar farms, or you can place them in places where there's congestion on the grid, so there isn't enough capacity on the grid lines to push the electricity through all the time. So you store it locally where that congestion takes place, and then you can fill your store, and then when the congestion is gone, you can then release it again. So you get a much more use of your grid infrastructure, or you can place them near where you've got the demand, and so you can store it while you've got excess energy coming through to the consumers, say maybe overnight, or if it's in an area with lots of solar during the day, and then store it for the consumers when the sun's gone down or the wind's not blowing. So it just gives you a vast amount more opportunities.
Basically, problem most of the energy solutions is you're unable to store it. Even hydroelectricity, we think we are turning on a switch and, we're getting it, but these are these turbines which are turned on and off based on the demand. There are very few ways to store it. The solar, wind has its challenges. There are some solutions now to store solar and wind, but like you said, the grid is crowded often, and you still, though you generate it, you're not able to store it and use it as required.
There's no real way of storing an electron. When you've got the electrons flowing, you've got to push enough electrons in at one end that you're using at the other. And if you want to store it in between, if you're pushing in too many electrons from the generators, and there isn't enough being taken out at the other end, you have to take it out and you convert it into something else. And so battery is a electrochemical system. So you're going from electricity through a chemical reaction. And then when you want it back again, it's a chemical reaction that delivers it back. For us, we're using a mechanical potential, so using gravity's potential to store it in a different way. And you can store it as heat or cold, but you have to change it. You can't just keep hold of an electron.
The way I'm visualizing it is that the kids have slime. Your product is almost like slime, and it's going at such a slow pace that it's holding on to the energy and going up, and then it comes down, and it has captured all this energy on its way up. Is that correct?
It's a good analogy, yes, but it's actually not at all like slime. So for American audience, it flows like half and half. Flows like a cream or something, and that you might put in your morning coffee. The thing about creating something that is much more slime-like or honey-like or something like that is viscosity is not your friend. When things are viscous and sticking to the sides, it takes more energy to move it. You get losses in the system from having something very viscous. So high density is great and low viscosity is great.
What about this liquid? Is it toxic? Is it safe for the environment?
Even though we're in a closed loop system, that's something that you absolutely need to do is you don't want to ever have a spill, and you put in lots of managed systems to make sure that doesn't happen. But you have to plan for the fact that something sometime will go wrong. And so the fluid has to be environmentally benign. It has to be non-toxic, that if you did have a spill, then it would absolutely not kill fish, or there would be no damage to the environment as a result of that. Those are some of our key criteria for our high-density hydro. I remember when I was talking about the reduction in vertical elevation, I had a second point I was going to make about the advantages of a high-density hydro system, which was rather than reducing the vertical elevation, the other thing you can do is make projects volumetrically smaller, proportional to the increase in density. And this gives you a huge opportunity for cost savings. So if you can reduce your construction costs by 60%, and in a traditional pumped hydro energy storage project, roughly 65% of the cost of a project is civil engineering. So if you can reduce that cost by 60% because it's volumetrically smaller, suddenly you have an economic advantage. Now, we do have to buy the fluid, which cancels out a proportion, or depending on the vertical elevation, depends how much of a proportion it cancels out. It gives you a huge opportunity for cost saving. And then when you put together the cost savings and the reduction in the height, then suddenly you can think, well, actually, we can start manufacturing these turbines for our high-density fluid in more volumes, which means that you can then commoditize them and drive the cost down of the project.
Your system is almost like a closed-loop hydropower system. It's almost like self-generating. There's no need for new inputs, and hence the low marginal cost of generating more energy. How does it work?
One of the, exactly as you described, it's a closed loop system. So you take renewable energy, you run pumps, you push the fluid up a relatively small hill, keep it there until you need the energy back, release it through turbine and regenerate electricity. The principle is very simple. One of the real advantages of the creation of a high density fluid, of creating your own fluid, in addition to the reduction in vertical elevation and in addition to the shrinking of the project, because it's a closed loop system, suddenly you can take this to a place where there's water shortages because it's closed. So traditional pumped hydropower is in places of high rainfall almost exclusively. So that's around 25% of the world's land area. So suddenly we have a closed loop system so we're not subject to evaporation in the same way. We can go to a desert or a desert city and actually put these type of projects. So the Middle East is a potential market for us, or parts of North Africa, which are really hot and dry, parts of the United States, where you would never put a traditional pumped hydro project. Suddenly there's a pumped hydro-like solution that you can place in the 75% of the world's landmass that are not suitable for projects with water. The advantages are not only the lowering the vertical elevation, but it's just opening up the opportunities across the world for projects where they wouldn't have normally had them. So we find that very exciting.
So are you the inventor of this solution?
It came about from a conversation between myself and our now CTO, someone called Tamas Patani, who's based in Montreal in Canada. So we do our mechanical and electrical engineering in Montreal. And the reason why that's such a good place is because it's the heart of the North American hydropower industry. So there's a great skill base that we can find for those type of engineering in Montreal. But the start of it came about from a conversation where Tamas and I had been going to various different energy conferences, and everyone was going, renewable energy, the future, we need to completely decarbonize the grid, and it's going to be wind and solar and hydropower and tidal power and wave power and all these other solutions. But we're going to have this variable supply and variable demand, and we need something to store it. And the answer to storage is batteries. There was no mention of any other solutions out there, even though at the time, 95, 96% of the world's energy storage was pumped hydro by power. And if you then look at it by energy, which are two different things, then it's over 99% of the world's energy storage is pumped hydro. And so I picked up the phone to Tamas, or it might have been an email, can't remember, but we just started talking. Why is this industry that is so mature being entirely overlooked in the energy transition? What is it about this industry? And then you look at it and you go, well, it's lack of available sites, it's water abstraction, it's the fact that the sites are far from people, so you need new power infrastructure, and the rarity of sites means that once you found a good one, the incentive is to build it as big as possible, which means that they take years to construct, and you often need government backing to do them. And so it's a very slow-moving solution to the energy transition. So we just asked ourselves the question, well, you have this such a mature industry with its existing supply chain. Is there anything you can do with innovation? Because that's what I'm in Tamas and interested in, to bring this 20th century industry into the 21st and help with the energy transition. And so we were talking, and eventually the suggestion came about saying, what if we increase the density of the fluid? And Tamas said, well, the theory is that you'll get the performance increase proportionate to the increase in the density. And then he said, I have no idea whether it's possible or even exists, or, we should have a look into it. Is there a fluid that can do this? Is it environmentally benign? So that was the starting point.
How did you increase the density? What is the basic fluid that you used first?
We looked at lots of different things, and there's some interesting very dense fluids which are either toxic or phenomenally expensive. Mercury would be great with 13 times the density of water, but it's not so good environmentally or availability or cost-wise. So what we ended up with is it's a suspended solid in water. So we create a fine powder, we add various chemistry and ingredients to that, and what that does is make the particles repel each other in a solution. So a bit like when you put two north magnets together, they push themselves apart. So it's the same sort of effect, but in the solution of these particles repelling each other. That's how we create a stable suspension in water.
Could you use wastewater?
So we can use any water. So the fluid is an engineered system as well. So you have to bring the water into a certain envelope or understand what that envelope is. So yes, you can use salt waters, but you probably have to treat it a bit to get it within the envelope. And at the moment we're using one mineral which is widely available to us. But our intention going forward is to find other industries that have used these same materials that we can take from those industries and reprocess them into our fluid. We're also looking to expand the range of minerals that we can use, which does change the density, but if it's very local to where you want to build a project, then that's good. And then where we ultimately want to get to is whereby when you construct a project and the rock that you take out to construct the project, you process that into your fluid, or a proportion of that. You may not be able to use all of it, but there might be a proportion of it. So you actually use what is on site to create your project, which is when we get to that point, and it's probably not every project you can do that on. Some of the rock would be not suitable, but there will be a good number of sites where that is possible.
Electricity that you're generating and you're storing, is that compatible with the existing system? Because the environment that it operates in is important for it to be made user-friendly.
Absolutely. You design your mechanical system, but then your electrical system to operate at the same frequencies and voltages that the grid operates at. And so you could either do synchronous generation, where you synchronize to the grid at 60 hertz and you just provide it at that frequency into the grid. So the grid doesn't know any difference. It could come from a coal-fired power plant or a wind turbine or a solar panel. They all do the same thing, that they match the grid. The other way you could do it is asynchronous, where you go through an inverter and then the inverter follows what's on the grid. So it relies on inertia from other parts of the system and it just follows whatever the grid is doing. So that's the difference between synchronous and asynchronous generation. And we could do either. You could probably do both on the same project by having part of your project set up in one way and part of the project set up in another. So maybe don't want to do that, but you could. As far as the grid is concerned, it's just seeing another generator providing with the same characteristics as all the other generators on the system.
The beauty of your solution is that the number of sites available for this application is far more, because you don't need the elevation that is required for water.
That's correct. And it's just the sheer volume of sites. So across North America, we believe there are somewhere around 350,000 sites available to us. So it's just a vast number of sites. And I know the UK better because I'm based there. So in the UK, it's around 6,500 sites. And then when you look at what the UK is likely to need in terms of energy storage by 2040, say, so not very far away, 18 years, that something like 300 or 350 projects, depending on their exact size, would provide 25% of the energy storage needs of the UK. So it's not a vast number of projects that you need to build to actually make a fundamental difference. So in somewhere across North America, I haven't got the exact number in my head, but something like 350,000 sites, 4 or 5% of those, again, can provide a similar level of energy storage, 25% of the US needs. And that's true of all countries. But what is also true of all countries is there are some places which are much better than others, because you still need the vertical elevations. And in the United States, there's some bits which are very flat. And those locations are not great for us. But also in those locations, you get mines, you get large quarries. So there is man-made activity whereby you can probably reuse some of those activities. So even in flat areas, there are good sites available to us.
So you're saying you could take an abandoned site in Indiana where it's flat and use your solution to get the elevation that you want. But the demand for renewable energy is also increasing as we try to wean off gas. But right now, there is not, if everybody decided to become electric, there is not enough electricity to power all our needs. So the solution like yours is required now, because not only to help the present consumption of electricity, but as we wean off gas, as we wean off petrol, we need the electricity, various ways in way we can generate, store the electricity locally, and to be available and accessible to the people who are transitioning.
Absolutely. And taking a step back, when the wind blows and the sun shines, you need to generate more than you need. And then generation that you've not used at that point in time, you need to capture it in some way, and it will be captured in different ways for different purposes. So some of it will be converted into hydrogen, and it will be used for industry or mobility and fuel cells, or it will be used in certain ways. Some of it will be stored in a system like ours, high density hydro, others which will be stored in battery solution of different types. And there are other solutions as well. And there's no one solution that can do it all. Just because of the sheer scale of what needs to be done, that no one company is going to scale at the type of size. And there are different solutions for different locations for different durations. So lithium-ion batteries are really good for relatively short durations, 2, 3, maybe 4 hours. Something like green hydrogen would be great for your interseasonal storage, because you've got uses for green hydrogen for mobility and heat and industry.
Has your application been implemented somewhere?
Yeah, we're just about to start building our first project in the first part of next year. So we hope to start digging in May 2023. So 6 months away is when we're.
And where is that?
So that's in the southwest of the UK. So it's at an operational mine in the UK. So the advantage of that, things like you've got existing security that you don't need to worry about that. But yeah, it's going to be a great project. It's still relatively small for us. It's a 500 kilowatt project, so and will operate for 2 hours. But that is a really good first step, and then once that's operational, we expect to go to something like 10 times that size a year later, and from there into commercialization. And one of the advantages that we really feel in terms of scaling is just the fact that our supply chain already exists. We don't need to build gigafactories because there are companies across the world that make pipes, and they might make pumps, and they make turbines. So we can find them on every continent, and the design is different for our high density hydro, as you would expect, but the manufacturing skills and the manufacturing plants already exist. So our ability to go from small volumes to large volumes is actually a relatively simple task for us. We're not building a new gigafactory for a new battery chemistry.
What is the scale of the problem that you're trying to solve?
That's a good question. Today in the world, we have somewhere around 170 gigawatts of energy storage. 95% of that is pumped hydro. It's that sort of number anyway. Industry commentators, I can't remember who this is, but it could be the IEA, or it could be the Long Duration Energy Storage Council, or one of these other consultancies. I can't remember exactly who it is. So industry commentators have recognized that from the 170 gigawatts that we need today, by 2040, we need around 2,000 gigawatts. So this is a more than 10 times increase in 18 years, which means that every 12 to 18 months, you need to replicate the entire world's energy storage that was built in the 20th century every 18 months. Just the scale of the problem is absolutely vast, which is why I was saying that you can't rely on one solution to deliver it. That traditional pumped hydro, they'll do some. We hope we'll do a lot. Batteries will do some. There are technologies that look at compressed air. You need it all. You need the green hydrogen. So it's trillions of dollars are going to need to be spent on it. And so the incremental cost of going from a system based on coal and gas, as those plants retire, the incremental cost of replacing it with renewables plus storage, it's not that significant a percentage. And so the cost to the consumer is unlikely to grow. In fact, it was more likely to reduce because once you've built a renewable energy project, the marginal cost of production is negligible. And the same with an energy storage project. Once you've built it, the marginal cost of storing it and reproducing it is again negligible. And you'll also decarbonize the power grid and hopefully mitigate the worst effects of climate change.
Can you work in conjunction with solar and wind?
Yeah, we see that as a very early opportunity, one of the earliest opportunities. And that's why I'm in Warsaw, is to go to a solar conference to talk about that. Solar and storage is what we're talking about over the next 2 days. And what you have we're talking about a solar project, is as more and more solar projects are built, that the revenues that the owner of that project can earn declines because other people are building solar projects. So you're all generating at the same time. So the revenue earned goes down to the point where it no longer becomes economically viable to bother to build the project or to generate. And so you then go, okay, well, it's still a cheap solution. If only I can shift the time, or as the industry calls it, change the dispatch shape of your energy. And so this is where energy storage comes in. So you can co-locate with something like a solar project, or you don't even need to be on the same site. You can be, within a few miles of it, and you can run the power between the two. And so you then store what you don't use, or you choose to store because the prices are too low. A project owner will go, the prices are too low. They might even be negative, the prices, because prices do go negative. The owner might go, well, I'm not going to sell it at a negative price. I will go and store it until the price rises back up. And we're confident that within a few years, solar projects without storage will be increasingly unviable. They won't be able to capture the prices in the market unless they've got storage, because everyone else will be generating at the same time. And so you need to change your dispatch shape so that you can provide the power when the prices make the project economically viable.
Actually, we are in the process of building a sustainable home here in Buffalo, New York. And with solar panels, we will capture only 39% of what we need because of, the shorter days. And then in summer, we have long days, but the problem is there is no way to store that for the needs in winter.
There are a number of solutions to do that. There are residential energy storage solutions, so you can go down that route, or
they're not that efficient, I've heard.
Not necessarily, and also quite costly. But again, there are increasingly developed sharing schemes around communities, and whereby a community together will do something that at a larger scale that benefits the whole community. There's some really interesting work in the UK about how to create those shared generation assets, wind and solar, and it will come fairly quickly how you create shared storage assets, and then everyone benefits from that. Everyone gets low-cost renewable energy that they own. They can sell to the grid, because often the grid is the owners of the grid. They're not very interested if you or I, as an individual householder, have got a bit too much solar power. They're not really very interested in buying it, partly because they've probably got quite a lot more from other people who are generating it. And so you tend to just have to give it to them, find a way of using it. But if there was a community doing that together and you were sharing that, then your ability to share it around as different households or even local businesses have different energy profiles, then you can create a very interesting local economic which is great. A friend of mine described it as the democratization of energy.
So you've received some funding from the UK government. How much have you received thus far?
We've been awarded £9.5 million in the last few months of UK government funding, which is, great. Thank you very much. And we're just in the process of gearing up our management systems to start spending, and we're actively recruiting, where we have project managers on board. We're placing orders to do the work to deliver and build those projects and that work. So it's a really exciting time, and it's really meant that as a business we're accelerating very rapidly. We're having to hang on with our fingertips to stop falling off at the moment.
So this is a question that I ask several guests who are solving a problem as large and as impactful. Not only large, but it'll impact our climate, our living. Have you patented this technology?
We have had one patent fully granted just recently, and I am going to let you be the first to know we've just had our second patent fully granted just a few days ago. And we have a whole pipeline of other patents across the various subsystems that we're working on. So we're developing patents in fluid formulation chemistry, and then in how to manage that fluid over time, because it's an engineered system, so you need to manage it. And then in turbo machinery, the fluid affects turbo machinery, so you need to develop your engineering of a traditional pump or turbine. It needs to be evolved for a high density fluid. Then control of the system and the whole system design are all areas for patents and IP for us.
With all these patents, what is your business model? Will RheEnergise set up all these plants, or do you have a licensing model?
Our core model is a licensing model. We want to make a difference to climate change, and the way we see to do that is to enable other people to build projects globally, simultaneously, and make sure that we license our IP to them and then help facilitate those projects. So that's how we see scale happening. It doesn't prevent us from potentially developing our own project pipelines and exploring other business models, but our key idea is let's get lots of people building these projects in lots of countries simultaneously.
Thank you again for coming on Mindful Businesses. We are talking to Stephen Crosher of RheEnergise. Thank you, Stephen.
Thank you so much, Vidya. It's been a pleasure.
We would love to hear from you. send us a voice note or an email with your questions or comments to info@mindfulbusinessespodcast.com. Subscribe, rate, and review us on Apple Podcast. If you learned a thing or two from this episode, share it with one friend. We recorded this episode in Buffalo, New York. Our theme music was composed by Tatum Gale. Our marketing assistant is Roseanne Korean. Our advisors are Jim Stone and Anupama Pashrija. This is Vidya Iyer with Mindful Businesses.